Hello everyone, my name is Isman Khazi. I'm Research Associate at Institute of Microsystem Technology at Furtwangen University in Germany. I welcome you all to this presentation of our poster titled Microfabricated Eddy-Current Sensors for the Non-Destructive Detection of Micro-Grinding Burn. So I will quickly share my screen, or I will show you the poster. Okay, the main goal of our research work is to investigate the feasibility of using planar fabricated eddy current sensors for the non-destructive testing of grinding burn. Moving to the concept of non-destructive testing using eddy current sensors, the fact of relative permeability being predominantly influenced within the grinding zone of grinding burn for ferromagnetic materials is exploited by the eddy current sensors reported in this work. The principle of eddy current testing is shown here in figure 1a. And another interesting point with respect to the driving frequency of eddy current coil versus the penetration depth or the skin depth of induced eddy current is shown here in figure 1b, wherein by varying the driving frequency of the microcoils, the penetration depth can be varied, and hence an in-depth profile information of the grinding zone can be obtained. Moving on to the preliminary proof of concept. In this case, circular spiral and circular non-spiral planar microcoils were fabricated using soft ferromagnetic nickel-cobalt alloys, as shown here in figure 2 and figure 3. This one is circular spiral micro-coil geometry, and here are fabricated circular non-spiral microcoils with different turns. Apart from this, for the characterization of these microfabricated coils, reference grinding burn with varying degrees were fabricated on 42 chrome molybdenum 4 tool steel, as shown here in figure 4. Moving on to the experimental measurements, as shown here in section 4. The experimental measurements revealed on one side the typical inductive nature of the coils, wherein the impedance of the coil increased as function of driving frequency, and on the other hand, the impedance changed as a function of varying degree of grinding burn, which can be seen in the inset for both non-spiral and spiral microcoils, which were used for the characterization. Furthermore, another interesting finding was made in this work, that is the impedance difference, delta Z, when compared to reference workpiece surface, increased with frequency, thereby showing the superficial nature of the grinding burn. For a better representation of the results, normalized impedance at a driving frequency of 5 MHz as function of varying degree of grinding burn is reported or shown here in figure 6 for both non-spiral and spiral microcoils. The impedance is seen to vary as function of grinding burn, both in case of this coil geometries. And furthermore, one interesting thing is found that the impedance change is 10 times stronger in case of circular spiral microcoils as seen here. Therefore, the feasibility of using planar microfabricated eddy current sensors for the non-destructive detection of grinding burn is shown in this work. Even though the change in the impedance is just merely 3%, but it can be improved by using sender and receiver coil geometry, and there is an ample room for improvement for this concept. So finally, I would like to thank you for watching this brief presentation and wish you a nice day.